Hi, everybody. So our main goal for this section is to prove the classification theorem for finite abelian groups. But the classification theorem for finite abelian groups is a special case of a classification theorem for finitely generated abelian groups. And even though I'm not going to prove that more general theorem, the idea of a group being finitely generated is important enough that I think we should get it on the record. And so we're going to begin with just a discussion of what it means for a group to be finitely generated. So suppose you have a group G and a collection of elements of the group. So G is not assumed to be finite, it's just any old group. And the collection of elements isn't assumed to be finite, it's just any old collection of elements. Then the smallest subgroup of G that contains that collection of elements is called the subgroup of G generated by T. And you say that T generates that group. In practice, one way to think about this is, what is the small, so I give you, let's say your group is G, you're given G, and you have elements G1 and so on, maybe infinitely many. So they're indexed by some set. So if you have a subgroup H which contains all of these things, then what does it have to have in it? Well, if it's a subgroup and it contains GI, then it also has to contain GI inverse. And it has to contain any product. GI1, GI2, and maybe GIK out to GIN, and these have powers. They could be plus or minus 1, because you have to contain, if you contain a group of elements, then you have to contain their inverses and also any product that you make by forming inverses, but only finite products. Notice that this is a finite product. Even though there might be infinitely many elements at hand, if you just take the finite products of these things, then it's not too hard to see that this collection actually forms a subgroup. It may be a very redundant way of writing the elements in the subgroup because there could be cancellation in here. They might commute with one another. They might not commute with one another. But still, if you have all of these things, then when you multiply two such things together, you get another thing like that, which still belongs to the subgroup generated by T. So one way to think about a group being generated by a set T is it's the group that you get by taking all finite combinations of elements in the set and their inverses, together with the identity element. That's also in there. And that's the subgroup generated by those elements. And so, for instance, we've seen this in the case where we talked about the commutator subgroup in the homework problem, where you took your set T consisted of all the commutators, and the subgroup is the group that you get by taking all products of commutators. So this is kind of an informal definition. I think the right formal definition is you just take the smallest subgroup, the intersection of all subgroups of G that contains the set T. So let's look at some examples. Well, the simplest example of a finitely generated group is a finite group. Because if G is finite, then you can let T just be the collection of G. I should have said, what does it mean to be finitely generated? You're finitely generated if there's a generating set, if there's a set T, so that the group generated by T is the whole group. So even if G is infinite, if you can get every element of G by combining a finite set of elements, then G is finitely generated. So let's go back to my finite group. A group is finite. If a group is finite, it's generated by all of its elements. Certainly, because the collection of the smallest subgroup of G, which contains all of G, right? If H contained in G is a subgroup, and it contains all of G, that means that H has to equal G. And so therefore, it's finitely generated. So any finite group is sort of trivially finitely generated. The interesting ones are the finitely generated groups that are not finite. a really good example of this is the group, let's say, let's just for the sake of argument, look at Z cross Z cross Z, but you could take any number of copies. So let's let E1 be 1, 0, 0, E2 be 0, 1, 0, and E3 be 0, 0, 1. And now think about the smallest subgroup H, which is a subgroup of Z cross Z cross Z, but it contains E1, E2, and E3. Well, if it contains E1, E2, and E3, it contains N E1, N E2, and Q E3, where N, M, and Q are all integers. Because if H is a subgroup and it contains E1, then it contains minus E1. And it also contains E1 plus E1 plus E1 plus E1 plus E1 n times, so it contains any1. And if it contains all of these things, then it contains their sum. Because it's a subgroup and it contains those three things, so it contains their sum. But that's equal to the vector NMQ for arbitrary N, M, and Q. In other words, if a subgroup contains these three elements, then it has to be all of Z3. And therefore, Z3 is finitely generated. It's generated by these three elements, even though it's infinite. The last example is a little bit fancier. We talked about wallpaper groups in the symmetry group section. And if you remember how those groups worked, they were subgroups of the Euclidean group. They had a subgroup T, and T was isomorphic to two copies of Z. It was a lattice group. And the quotient was a finite group. So W mod T was isomorphic to F, and F was finite. In other words, there's only finitely many cosets of T in W. So this was an infinite group. How do you know that it's finitely generated? Well, you can choose W1 up to Wn so that the collection of cosets are given, this is all of the cosets of T in W, right? The cosets divide W up into pieces. These, even though the cosets themselves are infinite, there's only finitely many of them, indexed by the elements of what's called the space group, which is the quotient group of W by the lattice. Now, this means that any element W is equal to one of the Wi's times an element of T, because it belongs to one of the cosets, so it has to equal Wit, and T is automatically equal to T1 to the A, T2 to the B, where T1 and T2 are generators of Z cross Z, as in the previous example. So what this tells us is that W is generated by the Wi, and there are finitely many of those, together with T1 and T2. And that altogether is a finite set, and so the wallpaper group is finitely generated. But there are some infinite groups that are not finitely generated. And a good example are the rational numbers. And the reason it's not finitely generated is because the rational numbers have arbitrarily big denominators, and you can't get bigger denominators by addition. So let's prove this by contradiction. So let's assume that Q1 up to Qn generate Q. So each Qi is Ai over Bi, where Bi is not 0, and the Ai and Bi are integers. And we can assume the Bi, just for convenience, are actually positive. So if we consider all the things that we can get by taking combinations of the Qi, we would get the sum of Ni Qi, where the Ni's are arbitrary elements of Z. And this is a rational number whose denominator is at most B1 up to Bn, right? Because when you add up a bunch of rational numbers whose denominators are B1, B2, and so forth, and you put them over a common denominator, the common denominator, I mean, it might be smaller, but at least you can be sure that B1 up to Bn is a common denominator. So if you now consider H to be the collection of rational numbers of the form Q equals A over B1 times Bn, where A is an arbitrary integer. So this is, in other words, the rational numbers whose denominators are B1 up to Bn. This is a subgroup under addition, because if you add two rational numbers with the same denominator, you just add their numerators. The denominator doesn't get any bigger. So if you add two numbers whose denominator is B1 up to Bn, you get a number whose denominator is B1 up to Bn. Here, it might not be in lowest terms, but all that matters is you can write it as a rational number with denominator B1 up to Bn. So it's a subgroup, and it contains Q1 up to Qn. And so therefore, and it's a proper subgroup. It's not equal to Q, because there are plenty of rational numbers which have bigger denominators. So we've shown that the collection Q1 up to Qn does not generate Q, because it's contained in a subgroup which is proper. And therefore, Q is not finitely generated, because we thought we had finitely many elements that could generate it, but they can't. That's a good example to keep in mind. It gives you a picture of how it can happen that a group isn't finitely generated. It's one of the things that can go wrong, is that when you can divide arbitrarily, it tends to spoil the finite generation. And now let's look at one other example. Suppose you have a finitely generated abelian group, like Z to the n. Then every subgroup of that group is again finitely generated. So if you take an arbitrary subgroup of Zn, it's going to again be finitely generated. I'm not going to prove that. It's kind of a result really belongs maybe in a different abstract algebra class, but it is true. But if the group is not abelian, then this fact is false. That is to say, you can have a finitely generated non-abelian group which has a subgroup which is not finitely generated. And there's a nice example of this here, which sort of ties together some of the things that we've done before using matrices. So we let G be the group which is generated by these two matrices inside GL2 of R. So I'm not going to worry about what that group is. It's just everything you can get by multiplying A, B, and let me just remind you what B inverse is. It's 1/2, 0, 0, 1. And what A inverse is, it's 1 minus 1, 0, 1. So you take everything you can get by combining A's, A inverses, B's, and B inverses, taking finite products. And that's a subgroup of GL2R. And if you think about it for a minute, you could see a few things about it, like it can contain, everything in there has determinant of power of 2. Because A and A inverse have determinant of power of 1, and B inverse have determinant 2 or 1/2. And so when you multiply these things together, you're going to get a bunch of 2's and a bunch of 1/2's, and they're going to cancel, but whatever's left is the determinant. Not so important. Now we're going to make a subgroup of this group. And it's just everything in G with 1's on the diagonal. Now, it's not too hard to check that no matter how you multiply these matrices, they stay upper triangular. So this is equivalent to saying you want to take the matrices which have determinant 1. But it doesn't matter. We're just going to, so inside G, we just take everything which has a 1s on the diagonal. So H is the collection of matrices 1, 0, 1, star. Star can be anything in G. So what do we know about H? Well, we don't have to figure out everything about H. Here's what we know about H. First of all, we know that if you have two elements in H and you multiply them, you add their upper entries. That's the first thing we know. And the second thing we know is that if we look at B inverse AB, which is 1/2, 0, 0, 1, 1, 1, 0, 1, 2, 0, 0, 1, this is 1/2, 1/2, 0, 1, 2, 0, 0, 1, is 1, 1/2, 0, 1. This is an element of H. And similarly, if you work out b to the minus n, a, b to the n, you get 1, 1 over 2 to the n, 0, 1. And that's also an element of H because it's an element of G because it's a product of B's and A's and B inverses and A inverses, but it has 1s on the diagonal, and that means it's an element of H. And so now we can see that H is not finitely generated because take any finite collection 1x, 1, 0, 1, 1x, n, 0, 1 in H. Those x's have a maximum. I mean, if we now think about what happens when you, because of this rule, if you look at, so this is an abelian group. I should have maybe mentioned that, right? This addition law doesn't matter. So when we think about all combinations, we're getting x1 to the n1, 1, 0, 1, x2 to the n2. I shouldn't, yeah, let's not use n. Well, whatever. 1, x, n, 0, 1, n sub k, n sub n, j sub n, j sub 2, j sub 1. What do I get here? I get 1, 0, 1, and I get the sum of ji, xi. Because that's what happens when you add. Here, if I do this j times, I get j times x1. Here I get j2 times x2, jn times xn, multiply them together, and I add. And so we see, just like with the rational numbers, that the denominator of every x, so that 1x, 0, 1 is in H, is at most the product of the denominators of the xi. Say that's D. Right? You have a finite list of numbers. They're rational numbers. And you have taken their combination. You're going to get a denominator which is at most something. But you know H contains 1, 0, 1, 1 over 2 to the m for arbitrarily large m. So there has to be an element like this which is not in the subgroup generated by these finitely many things that you got, because the subgroup generated by the finitely many things, the denominator can only be so big, and you can always find an element with a bigger denominator. I guess maybe I should have been more careful to say that the upper right-hand entries are all rational numbers. But if you think about multiplying together these matrices, everything here is a rational number. And when you, no matter how you multiply these matrices together, all their entries are going to be rational numbers. So the x's that occur, we don't have to figure out too much about them as long as we know that they're rational numbers. So it's the proof here that it's not finitely generated is very much the same as the idea for the rational numbers, that because you can use b to the minus n to get arbitrarily high powers of 2 in the denominator in the upper right-hand entry, then if you just take a finite combination of those things, you can't ever get all the denominators. And so the group is not finitely generated. So this is an example of a subgroup of a finitely generated group, which is not finitely generated. And the key fact about it is that the group is not abelian.